In this video, we're going to talk about potential energy, kinetic energy, and how that relates to temperature. The two major forms of energy that we're going to talk about in this course are potential energy and kinetic energy. Potential energy is stored up energy. It is energy that is found by virtue of its position in a force field or gravitational forces or by composition if it's a chemical bond. And kinetic energy, which is simply the energy of motion. Let's explore each of those individually. But it is important to note that we can change from one type of energy to another. Sometimes one potential energy to another potential energy, sometimes one type of potential energy to kinetic energy. And of course, kinetic energy can be changed to another type of kinetic energy, or it can be changed into potential energy. So we can change between the types of energy, but they are different types. We'll look at some examples of potential energy first. When you see the word potential, it means that it has the potential to do something. Currently, it's not really doing anything. It's just waiting to be released or used. So we say this is energy by virtue of position. Normally, we're talking about something like, let's say I have a ball at the top of a hill, and it's about to roll down. While it's sitting there, it has stored up energy. If I push it off the edge, that energy is released, and now it's doing something. That's going to be considered kinetic energy. But while it was sitting at the top, it had the potential to fall, and so it had stored up energy. The water behind a dam has potential energy. It is being stored behind that dam. As it starts to fall over, it turns into kinetic energy. Then it turns a water wheel, which turns into electrical energy, another form of kinetic energy. In a similar way, when you have an electron that is stored away from a proton, they have a positive and a negative, and they're attracted to each other, but they're being held apart from each other at different layers. As they fall down, they're going to release some energy, usually some light energy. We'll see that later in the semester, but basically we can see that there are different levels, and so within the atom itself, there is potential energy depending upon where those electrons are sitting. The more challenging version of potential energy is the one that is built by its composition. So you probably already know if you take a piece of wood and you start a fire, it will give off both light and heat energy. Those are two more forms of kinetic energy, but the wood itself had stored up energy, so it had potential energy. That is because of its chemical bonding pattern. When it releases those bonds, it gives off energy. Very similarly, we could have a battery, where a battery has two things that are close to each other that want to do a reaction, but we're keeping them separate by something. When we connect the battery, it allows the electricity to flow, and that energy is released when those two things can now react. Once they're reacting, we have a flow of energy. Now that's kinetic energy again. So these are all examples of potential energy. The ball at the top of the hill, the water behind a dam, the electrons being held away from the center nucleus, the log, the piece of wood, anything like that, and the battery are all potential energy. They can be changed into other forms of energy, but right now they're holding on to that energy and they're storing it, ready to be used. While potential energy is the energy where something is getting ready to do something, it's holding it, it's storing it, kinetic energy is the energy of motion. It's where things are actually happening. So somebody's walking or a car's driving, bicycles moving, any of those things would of course be kinetic energy. That doesn't seem like it has much to do with chemistry, but what we're looking at in chemistry is we're going to look at very, very small particles and see that they are constantly in motion. So those particles are moving around. You can't always see it, but they are moving. Sometimes they're just shaking, sometimes they're moving rapidly. We also know that the electrons are moving around the nucleus. That's all a form of kinetic energy. So there's always kinetic energy happening around us. We just don't always notice it because it's very, very small. Kinetic energy is dependent on both the mass and the velocity of an object. So let's look at each of those in a little more detail. First, let's look at how the mass is related to the kinetic energy. I like to make these models for you in the size that you can imagine rather than in small sizes like the size of a particle, and hopefully this will give you a better idea of how kinetic energy is related to both the mass and the velocity. To see the relationship between the mass and the kinetic energy, we're going to use a set velocity. Recall that velocity is similar to the word speed. So when I say how fast something's going, we call that speed. But when we say how fast and in what direction, we call it velocity. So we're just going to use the phrase speed for what we're doing, just to keep it simpler and make it more obvious to you. I'm going to use an example of a VW bug and a semi-truck. They are both going the same speed. They're both going 60 miles an hour. They both stop all of a sudden. Which one had more kinetic energy? So in order to see that, you would basically look at what happened to the wall, that you hit a wall. What happened to that wall when you hit it? So clearly, when the semi-truck hits the wall, it just barrels right through it. It may eventually stop, but it's going to knock down a whole lot of that wall. The VW will probably just get crushed a little bit, might break down a little bit of the wall. So the big difference there, you should see that the semi had a lot more kinetic energy. Now that it's stopped, it no longer has that kinetic energy. But the original vehicle, because it was much more massive, had much more kinetic energy if it's at the same speed or velocity. In chemistry, rather than using a VW bug and a semi-truck, we might be comparing something like helium and argon, two very different noble gases, but we know that one is much more massive. So the helium is very low mass, whereas the argon would be a high mass. Now let's look at the velocity. In this case, we're going to use two things that are the same mass. Let's say they're two VW bugs. One's going 10 miles an hour, and the other one's going 50 miles an hour. Sorry for the excessive violence, but now we're going to crash into a wall again. Which one will cause more damage? The one that's going 10 miles an hour or the one that's going 50 miles an hour? Well, hopefully you could guess that the one that's going 50 miles an hour will do far more damage. So here we can see that at the same mass, the higher the velocity, the higher the speed, the more kinetic energy is present. And importantly, the more kinetic energy there is, the faster something has to go if it is the same mass. In chemistry, that's important because we can see that the more kinetic energy is present, the faster something will move, or we can see, of course, the other direction. The faster something's moving, the more kinetic energy it must have. Now, what happens when I have the same kinetic energy and I'm looking at the comparison of mass and velocity? In this case, I'm going to use objects of two different masses. Again, we're going to use the VW bug and the semi-truck. I give them each 1 gallon of gas. Let's say that's how much energy I have currently as potential energy in the form of gasoline, but once it starts moving, it turns into kinetic energy. So we're going to give them the same amount of gas, and we're going to see which one will go faster. So given the same amount of energy, good engines, whatever you need, we're going to hit the gas, and we'll see which one should go faster. And I would imagine you could guess that the VW bug will go faster than the semi-truck, and that is because the semi-truck is so much more massive. And again, when we look at speed, we're looking at something related to velocity. The faster it goes, the higher the velocity it has, assuming they're going in the same direction. In chemistry, when we look at the kinetic energy, we're going to be measuring it by using the temperature so that we can find out how fast those particles are moving and their masses, and that will tell us the kinetic energy. So the temperature is related to the kinetic energy. And now it's time for you to try it. You need to indicate whether each of the following is a type of potential energy or a type of kinetic energy. Please pause your video while you answer these questions. Let's start with letter A. We have a car parked on a steep hill. In this case, the car is parked. That means it's not moving. It has the potential to roll down that hill, and so this has potential energy. Letter B. A tennis ball rolling across the court. Here we can see that the tennis ball is rolling. That means it's moving, and so we have kinetic energy. Letter C. A picture hanging on the wall. The picture's just hanging there. That means it's not moving. That tells us it has potential energy. It has the potential to fall down. It has gravitational force that could pull it down, and so this is potential energy. Letter D. A piece of coal before it's burned. Since it says before it's burned, that tells us it has the potential to burn, and that tells us that it is potential energy. Letter E, a roller coaster rolling. If you see a roller coaster rolling, that means that it is moving, and so again we have kinetic energy. Letter F, a rocket flying to the moon. Again, the rocket is moving, it's flying, and since it's in motion, then we know that that is kinetic energy. Letter G, a fan cooling a room. This one's not quite as obvious, but again, because it's cooling, that means it's turning, and so that one is kinetic energy. Letter H, leaves blowing in the wind. Again, these are moving around as long as the leaves are moving, and that means that there's kinetic energy. Now, those particles of air that are blowing into the leaves also have kinetic energy. And finally, I, a propane tank attached to a barbecue. And the propane tank is just sitting there. It's attached to the barbecue. It has the potential to produce fire, but right now it has no fire, and so this one is potential energy. Temperature is a measure of the average kinetic energy of the particles, whatever particles you're measuring. The Kelvin scale was developed to express the mathematical relationship between temperature and kinetic energy. They aren't exactly equivalent, but they are related to each other. One of the important things about the Kelvin scale is the number 0. So 0 on the Kelvin scale is the point at which we have absolutely no more kinetic energy. We've never actually reached 0 on the Kelvin scale because it's impossible to reach, because there's always some sort of kinetic energy, even if it's just the electrons moving around the atom. We know, though, that all particles that have the same temperature, no matter what their size, they have the same average kinetic energy. So if they have the same kinetic energy, but they have different masses, that means that the velocity must be changing also. So if they have different masses, they will have different velocities, but we know that they have the same kinetic energy at the same temperature. So let's look briefly at some relationships between temperature, kinetic energy, mass, and velocity, and see what happens. So if I tell you I know the kinetic energy, then I know everything in that container has the same temperature. If I tell you I know the temperature, I know that everything in that container has the same kinetic energy. So those two are related to each other directly. Whatever I say, they're going to be at the same energy level and the same temperature. Then we'll look at the mass. If I have two things with different masses at the same temperature, you should be able to tell me which one's moving faster. So I'm going to have one that's lightweight, like helium, one that's heavier, like argon. Which one will move faster? As you might guess, the one that's smaller, lighter weight, is the one that will move faster. It'll have a higher velocity. And now let's go the other direction. Let's say that we have two things that have the same velocity. What does that tell you about its mass? What we know is if it's the same temperature and the same velocity, they must be the same mass. So all of those would be the same. Those two things would be equivalent. What happens if I increase the temperature? What will happen? Well, we know that the velocity will increase. The velocity or speed of those particles should increase. And of course, if I decrease the temperature, then we know that those particles will go slower. And now we're going to talk a little bit about the kinetic theory just to introduce it. The kinetic theory is the name given to the concept that all matter consists of particles in motion. That doesn't matter if it's a solid, a liquid, or gas, all of those particles are in motion. And we're going to talk specifically about how the kinetic theory applies to solids, liquids, and gases, and then how that affects things in our world. There's a little bit of evidence that these particles are in motion. It's very easy to see for the gases. So if we look at a leaf blowing in the wind, why is it moving? Well, that's because the particles of air are bumping into that leaf and making it wave around. We can feel the wind blowing on us. So those are things that are telling us, hey, those gas particles have to be moving. So we know that that's happening. If we look at liquids, when we put a drop of food coloring in the water, we see that it blends throughout the liquid even without stirring. So we just put one drop in, it'll spread throughout the liquid slowly. That is telling us that those particles are moving. In this case, we know that one water particle is hitting one food coloring particle and making it bounce out of line and move around in the container, and then they're bumping into each other and kind of moving all around. Eventually, the whole thing will become the same color in the container because of this particle motion of liquids. What about solids? Well, solids are really hard to see. Because solids hardly move, there's very little evidence of their motion. But we do know that they are still moving, and part of that is from our realization that at any temperature, if there's a temperature, there must be kinetic energy. So it can't have stopped unless it's actually reached 0 degrees Kelvin. In the next set of videos, we're going to talk about the gases, the liquids, and the solids, and how kinetic theory applies to each of those.